Let me share the screen. So fine. I hope I am audible now. Fine. Uh, so good afternoon once again. I think that's the fourth day and the last session of the fourth day. Lot of discussion has been done on the theoretical aspects of generative AI. You must have gone through different models, different type of algorithms. Comes under the umbrella of generative AI, starting from variational autoencoders, generative adversarial networks, GANs, uh, LLMs. You must have studied transformers. You have also gone through uh, diffusion algorithms for image generation. So now it's time to use these algorithms or these models. And this particular session is dedicated towards application of generative AI and the application specifically in the field of healthcare. So, first of all, I just want to disclose here that yes, I'm not a doctor. Uh, since the session is related to healthcare, but primarily I'm an engineer where trying to implement the concepts of AI in the field of medical or healthcare. And if if I do any kind of mistake related to medical terminology or anything related to the concepts of healthcare, so please forgive me. I just want to disclose here that I'm not a doctor. Fine. This is just a brief overview of the agenda which we will be discussing in this talk. Firstly, to give you more idea about how we can use deep learning or the modern concepts of AI in the field of healthcare. So we'll take some case studies and we'll see how we can train the models, how we can test the models, what are the challenges we face whenever we are developing these kind of models, and then we will see how these models which we have studied, like transformers, generative adversarial networks, diffusion models, large language models, how we can use these models in the field of healthcare. And in the last, I'll demonstrate you one or two research projects which we are developing in our lab. Now, to start with, uh, have you ever tried? I mean, you must have tried ChatGPT for different tasks like drafting the emails. Software engineers must have used ChatGPT for writing codes or finding bugs uh, in the code. But what if I ask uh, uh, medical related question to ChatGPT, and that is the example which I myself has executed. I gave a prompt that I have 101 fever and symptoms of cough and cold, and see what ChatGPT has given me as a reply. It has given me some of the possible reasons, and it has also uh, uh, suggested some of the cures related to this kind of these kind of symptoms. So that's how these generative AI based tools can help us in uh, addressing some of the healthcare problems. So now you can get an idea that yes, we can develop certain tools, and already different companies are already developing the tools where they can help the doctors. They can give you precise information related to a particular medical condition, can generate personalized treatment plans. So we'll see through this session that what all applications we can develop with the help of generative AI tools. I think the basics are already clear to you. Difference between AI, ML, DL, and generative AI. I don't want to again discuss these concepts, but I will straight away head to the main topic here. That is, so the story started here. The story started somewhere in 1970s. One of the scientists called Lodwick, Professor Lodwick, he developed a research plan in which uh, the research plan was related to computer-aided diagnosis and specifically in the field of radiology. And the idea was to use the computer application to develop some kind of computer applications which can read the radiology modality, and then it can generate some results. So that was the start of application of computer application, or I would say artificial intelligence in the field of diagnosis or medical applications. And for this particular work, in 1975, he received the nomination for Nobel Prize. And the work, the groundbreaking work which he did was modeling of images and the computer diagnosis of bone tumors. Now, you must have gone through different kind of use cases of AI. And nowadays, most of the bigger hospitals are advertising that AI-based robotic surgery, AI-based diagnosis, application of AI, automated surgery. There are a lot of applications, and which has become a reality, and you have started seeing them around you in the hospitals. So there are n number of applications. AI can be used for diagnostic tests. It can be used for interpreting your X-ray images, MRI images, computed tomography images, studying the genetic information, developing treatment plans, and so on. There are some of the use cases which I have gathered from internet, like deep learning AI discovers surprising new antibiotics. So this is very active research area. The discovery of new antibiotics, it's very active research area, and scientists are able to develop new antibiotics with the help of deep learning. Specifically, during the COVID time, uh, there were a lot of research which was done using deep learning to interpret the chest X-rays of COVID-19 patients, and uh, developing an alternative to the other COVID-19 testing plans. So, though there was a problem of shortage of available chest X-rays specifically for the COVID-19 patients, but the scientists were able to develop models which were correctly identifying infection from the chest X-rays. There are lot of applications, specifically if we talk about medical domain, a lot of applications of AI in these areas. As I was talking to you, there are large companies which are investing a lot in applying artificial intelligence in the field of healthcare, like Google DeepMind, which is now part of Google Health, and they have developed an AI model like AlphaFold, which helps in predicting protein structure, and which in turn aids in drug discovery and research related to certain diseases. And they have also developed AI models for eye diseases, and specifically, Google claims that they have developed a tool which can detect diabetic retinopathy with a human comparable performance. There is another Indian company which is coming up, started like Cure.ai, and this company has developed a tool which analyzes the chest X-rays and head CT scans, and it is able to detect the conditions like TB, tuberculosis, or brain hemorrhage. And definitely, these kind of AI-based solutions can help the radiologist to increase the diagnostic accuracy. Similarly, IBM Watson for oncology. There is Trust Stroke. It is an AI-powered decision support system that personalizes the stroke treatment by analyzing uh, the different clinical and imaging data of the patient. And the AI-based chatbot, and specifically generative AI-based chatbots are become popular these days, where the patient can write their queries, and the chatbots can reply to those queries till the time the query is very complex. Definitely, the chatbot can answer those queries, and they can determine whether they need to see the doctor based on the queries. Now, coming to a very basic approach, how we can use AI models in healthcare. Let's take a simple example of detection of COVID X-ray, and why can't we make a classification type of model where we provide a chest X-ray image, and this model gives us what kind of abnormality is there in the chest X-ray, and we can define different classes. Let's say COVID-19, pneumonia, or this chest X-ray is normal category, or we can add on uh, uh, multiple abnormalities or diseases here. So basically, we need to have a model. We need to develop a model which is capable of reading chest X-rays, and then once a chest X-ray is provided to this model, it is able to correctly identify what kind of disease, what kind of symptoms are there. Similarly, as I was talking to you, Google has claimed they have achieved very high accuracy in identifying diabetic retinopathy. So, diabetic retinopathy, you must be aware of. It's a very dangerous disease which can sometimes damage the blood vessels, and it can lead to vision loss. This particular disease is prominent in diabetes patients. That's why they are being advised to have a regular eye checkup. So, uh, unlike uh, examining the chest X-ray for finding tuberculosis or COVID-19, here specifically to diagnose the diabetic retinopathy, a retinal fundus image is taken, and now we can develop a model which can read these fundus images and then classify whether the fundus image is damaged or have a symptoms of diabetic retinopathy, or it's a normal one. And one of the very complex structure in human body is brain, and brain contains different type of fluids, and the volume of these fluids plays an important role in diagnosing different diseases. So MRI images can help us in identifying those abnormalities, and whenever we take MRI images, we need to segment those MRI images so that we can identify uh, different regions and the volume of different type of fluids, so that in turn we can find out what kind of abnormality is there. So with the help of different models, you must have studied in last 3 4 days, different kind of segmentation models can be used for the so that we can segment the MRI images and do the diagnosis. Then another type of application could be detection of cancer, and that uh, we do with the help of histopathology images. And these histopathology images are basically high resolution microscopic images of your tissues, and then we can train a model with the help of these histopathology images to detect whether the patient has cancer or. Now, how does these models being trained? What exactly they learn? How these models are able to classify uh, different modalities. So whenever a radiologist learns, whenever a radiologist is being trained, they are shown different kind of X-ray images. Let's say the radiologist is being trained to detect COVID-19 from chest X-ray images. So what do? We provide a lot of normal X-rays, as well as we also provide different X-rays related to COVID-19. And after seeing hundreds or thousands of X-ray images, the radiologist will be able to identify which X-ray belongs to which category. Now, suppose if we give an unseen chest X-ray to radiologist, he or she will be able to identify to which category this chest X-ray belongs to. Now, in the similar fashion, our AI models, our deep learning models can learn. So basically, providing examples means training those models. And once they are trained, we can provide any unseen X-ray, and these models will be able to classify those X-rays. So basically, we build models, and these models could be of any type. We have gone through these different type of models, and we train these models. These models learns from the underlying data. So this could be a supervised kind of setup where we provide thousands of chest X-ray images along with the labels, and then these models are trained. Once trained, they can be used further for deployment, and they can classify new chest X-ray. Uh, Now, in case of histopathology images, as I was telling you, they are very high resolution histopathology images. So instead of providing a high resolution image, what we can do is we can sample the patches from a high resolution images, and then train these models on these patches instead of training on a very large image. Now, there are different popular convolutional neural network architectures which are extensively used in the field of healthcare. Not only these, there are many more which are extensively used in specific type of classification problems in healthcare. Now, one of the major challenge we face, specifically in the field of uh, healthcare, whenever we are going to apply deep learning or artificial intelligence models in the field of healthcare, one of the major challenges the data set. As I was telling you, in the case of COVID-19, in the initial times, there was not much of chest X-ray images available for the positive cases. And as you are aware, we need to provide uh, labeled data to these models for training purposes. So if we have very less volume of data for a particular class, then there could be a problem in training, and there will be problem performance of these models whenever we are going to test them on unseen data. So in those kind of scenario, and specifically this problem is prominent in the case of healthcare, where we have very less data available, specifically in the case of, yes, I think someone has already mentioned in the comments that yes, the some of the organizations keep their data as private. So there are various ethical issues associated with medical data, and definitely whenever you are collecting medical data, you need to have an ethical clearance from ethical committees of different hospitals and labs. And surely, it's a big challenge. The data set size is always a big challenge in the field of healthcare. So you need majority of your time is devoted specifically in the collection of the data, and have ethical approvals whenever you create a new data set in the field of healthcare. Now, one of the possible solution for dataset side challenge is transfer learning. You must have heard about it. So transfer learning is nothing but we are fine tuning the pre-trained deep learning models, And this is applicable for any kind of deep learning models, not specifically convolutional neural networks. So this is generalized concept of transfer learning. We can fine tune some of the layers of the deep neural network. And so basically the idea is we train the deep neural network on a data set which have a large volume of images. And not only images, we can talk about any kind of modality, whether it is uh, text or audio or image. And so here, this slide depicts the concepts from a computer vision perspective. And so basically the idea is we train the deep neural network on the data set where we have a bigger data set, we have large volume of images, and then we call it pre-trained convolutional neural network. And then further, we can use this pre-trained convolutional neural network for our data set, which is smaller in size. And the idea is we just fine tune the later layers of the deep neural network, because the task of the initial layers, specifically if we talk about the convolutional neural network, is to extract very high level features. And whether it is image of cat or dog, or whether it is image of X-ray or MRI, the task of extracting edges, lines, corners is similar. So the same filters can be used for different type of images. So that's the idea of fine tuning when you face data set size challenge. Now, another very common way of solving this challenge, which we already do, is data augmentation. And this data augmentation, specifically in the case of medical, I mean, from computer vision perspective, we can apply different kind of image operations like zoom, flip, translate, adding noise, or combination of different operations. Now, uh, once we have developed this model, these models can be tested. And whenever we create a data set, this data set has three portions. You must be aware of these three parts. One is training, which is used for training the model or the development of the model. Validation, this is used for tuning the parameters during the training process itself. And the third one is the testing data set, which is used for evaluation of the performance of the trained models. Uh, Now, in testing as well, we do have different challenges, like how do we annotate the ground truths? So whenever we create a data set, definitely in a kind of supervised machine learning kind of setup, we need accurate labels for each of the image or the data point. So that's again a major problem here. Another problem is the patient data overlap. Let me explain that. Uh, so the idea is basically there should not be any overlap of patients in different type of these in these different sets. Like we should not have uh, data of a patient both in training and testing. So what does it mean? Uh, the data related to a particular patient should be either part of training or it should be part of testing. Why? Let me give you an example here. Suppose a patient goes for a chest X-ray and the patient is wearing necklace, although these kind of precautions are already taken while taking the X-rays. But yes, there might, I'm just giving you a simple layman example here to understand the concept. Like suppose a patient goes for a chest X-ray and he or she was wearing a necklace at that time. So uh, suppose at the first time that the patient goes in the month of January, and the chest at that time the chest X-ray belongs to a particular disease, and then the chest X-ray is becomes part of the training data set. Now, after 6 months, let's say that patient goes for chest X-ray again, and this time, suppose there is no disease, if there is no symptom of any disease in the chest X-ray of that patient, and let's say that that particular chest X-ray becomes part of the testing data set. Now, what happens here is uh, whenever we are training that model in which the chest X-ray, which was taken in the January month, is part of the training data set. Now, this model will learn a specific feature which is there for that particular patient and for a particular category. Now, if a new chest X-ray comes for that particular patient, it will classify into that specific category. So that's the problem with patient data overlap. So basically, we should ensure that there is no overlap of patient in different sets. Either they should be in training data set or they should be in the testing data set. And then there's a problem of ground truth annotation or the labeling of the data set. And there are cases where there is difference of opinion among the medical practitioners on specific modalities. Let's say the doctors are analyzing the histopathologic images on the microscopes, and there is a possibility that there is a difference of opinion among the medical practitioners themselves. So in that case, the consensus voting could be one of the options. So basically, labeling of the data is very typical one. So whenever a new data set is being created, it is always advisable to have the labeling of those images or labeling of those data sets from multiple medical practitioners, and then you should have a consensus voting. Now, evaluating the models. So one of the very common way of evaluation of the models is accuracy. And how do we define accuracy? So accuracy is the probability of correct predictions. And let's see an example here. Suppose there are two models, model 1 and model 2. And on the left hand side, you can see there are uh, uh, 10, suppose we are doing this testing for a model trained on histopathology images, which are classifying the images into malignant and benign category. So what happens here is, let me take the laser pointer. Yeah, fine. What happens here is, suppose we have taken five positive and five negative cases. Now, suppose model 1 classifies all of them as negative. However, the model 2 classifies some of them as positive and some of them as negative. So, in both the cases here, you can see the accuracy is 50%. Model 1 is classifying each of them as negative. However, model 2 is classifying some of them as positive, some of them as negative. However, it is classifying only 50% of them as correct. Both the models are giving you accuracy as 50%. So what do you think, which model is better here? Though the accuracy is 50% in both the cases, but which one is better? I would say model 2 is better. At least it is able to distinguish between uh, the positive and the negative modalities. But the point here is, the conclusion which I want to draw here is, accuracy is not the correct measure to evaluate the performance. I would rather say in another terms, we should use other performance matrices along with accuracy while evaluating these models. What are these matrices which we can use for evaluating the models? So basically, there are two, three more matrices like sensitivity and specificity. You all must have gone through this kind of matrix in which we have four elements. And on the left hand side, we have ground truth or the labels. And on the top, we have output of them. So basically, we draw this kind of matrix, and there are four parameters here: true, positive, true negative, false negative, and false positive. So basically, true negative tells you, uh, uh, suppose we are classifying chest X-ray, whether it is positive or negative. So the actual label of that chest X-ray is positive, and the model has also predicted it as positive. So that's the correct case, and that comes under the category true positive. And similarly, if the actual ground truth label of X-ray is negative, and model is also predicting it as negative. So these two cases are the correct ones. However, the other two are incorrect ones, where the label is positive, but the model is detecting it as negative. And similarly, the label is negative, but model is predicting it as positive. So basically, ideally, these false positives and false negatives should be close to zero. However, these should be high, true positives and true negatives. Based on these four parameters, we calculate two new matrices like sensitivity, which is a ratio of true positive divided by true positive and false negatives, the first row. And specificity, so it is ratio of true negative divided by true negative plus false positive, the second row here. That's the calculation here for a particular model for sensitivity and specificity. So basically the idea is, apart from accuracy, we must also use other parameters like sensitivities, specificity, F1 score for evaluating any of the models. So another kind of performance evaluation could be with the help of ROC curve. Now coming to different data sets, there are a lot of data sets available, uh, publicly available, which can be used for your research. Like for MRI, you have lot many data sets for different kind of abnormalities, different kind of diseases, like for autism, for Alzheimer, for Parkinson. There are different data sets available. You can freely access these data sets, train your own model, evaluate your models, and compare your models with other state of the art. For chest X-ray, there are n number of publicly available data sets which you can utilize. Similarly, for histopathology images, also you have large number of images. Fine. Now, this was about the basics. This was about the application of basic deep learning based models and in the field of healthcare. Now, coming to the generative AI perspective of healthcare, I think now I need not to repeat this definition here for generative AI, because all of you are going through it uh, in last 3-4 days, and I'm sure you are totally aware about what is generative AI and why we call it generative AI. What are different models under the purview of generative AI umbrella? And so I'm just skipping some of the basic part here. Yeah. So coming to different type of models, generative AI models from a healthcare perspective, let me introduce that. So we can have text to text models, and the idea here is they takes natural language input and produces the text output. And what could be the use of this kind of models? It could be translating patient education material into one language to another language, or maybe summarizing medical research paper in a plain language. Then the next type of generative AI model could be text to image, and these type of models are basically trained on a set of images, and each caption with a short description. And let's take a medical example of this kind of model, where what we can do is we can generate or we can edit an image and which explains a particular medical condition. Let's say I give a prompt that generate an X-ray image with symptoms of tuberculosis. So this type of models are capable of doing generating this kind of solution. And then we have text to video or text to 3D. And one of the example could be like generating a video and for a patient to demonstrate how to perform exercises at home. Let's say the patient has met an accident and the doctor has suggested certain exercises to recover from that accident. And so what we can do, we can give a prompt to this type of model to generate a video of depicting or describing or demonstrating a particular exercises to the patient. Now, you have talked about the foundational models, and I'm sure you are aware of what exactly these models are. Here also, like in from healthcare perspective, uh, we can have these foundational models trained on different type of modalities, medical modalities, and then they can be fine-tuned to specific tasks. Now, coming to a broader picture of generative AI use cases in the healthcare, there is a lot of information here on this slide. I think some of the terms you are already aware of, like GANs, variational autoencoders, LLMs, FBMs, EBMs. So I'm assuming that you are aware of these terminologies, you are aware of capabilities of these models. Now, what all we can do with the help of these models? Now, since it is generative AI, so we can generate the content, we can generate the data. So first of all, using these models, we can we can generate a realistic patient data and which can be used for research and training purposes. As I was telling you, we have dataset size challenges, specifically in the field of healthcare. So these generative AI tools can be helpful in generating realistic patient data, and that patient data can be used for research as well as training purposes in the medical settings. And also there can be different versatile applications of this generated data. Now, another application, uh, apart from generating this synthetic data, and another another aspect of generative AI is in the field of drug discovery. As I was telling you, new drug discoveries are very active area of research. So basically, these generative AI models can be used to generate novel new small molecules or nucleic acid sequences and protein structures with some kind of desired structure or the function. And in turn, these new discoveries of small molecules or nucleic acid sequences or protein structures, they can help us in different type of drug discovery. And that can help us in personalized medication of the patients. Now, another area which is very helpful is medical diagnosis. So these generative AI models, which can be trained on a vast data set of medical reports or images like MRIs, X-rays, CT scans, uh, they are capable of identifying patterns related to specific diseases. So, for example, like the generative adversarial network, they can be used for image reconstruction, image synthesis, segmentation, registration, and classification. Now, another use cases. Specifically, there are a lot of use cases of LLM, such as GPT-4, and one of the popular uh, LLM in the field of medical domain is Palm 2, developed by Google specifically for medical application. These LLMs can be used to generate summaries of patient data. You must have seen very thick files of patients who has long history of medication and diseases. Now, with the help of these models like LLMs, what we can do, we can generate the summary for a particular patient, and uh, this patient summary can be useful in healthcare settings where large amount of data are collected and that has to be interpreted very quickly and efficiently. Now, uh, how handy it would be if instead of having a very thick file of a particular patient in which we have different prescriptions, different medical reports, different uh, history of the patient, why can't we generate a summary of that thick file, and that summary could be handy for the doctor to have a precise medical diagnosis for a particular patient. So specifically in this kind of setting, uh, these LLMs could be helpful. And like the electronic health report, I gave you this example, the thick file. Let me put it in other words, like electronic health reports. They might contain the patient data, say, like medical history or what kind of medications they have taken in past, what kind of allergies the patients have, different kind of prescription, different kind of laboratory results. Now these generative AI models, specifically these LLMs, they can be trained to read all those electronic health records and understand the key points and generate a precise medical summary, which can be handy for the doctor to take decisions, to do diagnosis, to effectively give treatment to the patient. Now, another very important application of these generative AI models could be clinical documentation. Now, they can help us, to create personalized educational contents based on patients' specific condition or symptoms, or if the patient is asking certain questions. So, let me give you an example. Suppose a patient has diabetes, history of diabetes. Now, with the help of these models, we can generate information and generate information specific for that patient related to managing the blood sugar levels, what kind of diet that patient should take, what kind of exercises that patient should do, and what kind of medication should be offered to that patient. So this was one of the glimpse of generative AI uses in the field of healthcare. Now, coming to different type of modalities, I think we have already talked about some of the modalities, but those modalities were mainly related to image. But yes, we can have other modalities for these generative AI models, not only generative AI models, but for deep learning based models as well, like for natural language processing. Natural language kind of data modality could be your discharge history, your diagnostic reports, your prescription, uh, doctor prescriptions, and many more. In case of image modalities, we can have X-ray images, MRI images, CT images, and many more. In case of audio, we can have your stethoscope audios, and there could be other audio files, medical related audio recording, which can be used to train these models. Now, some of the use cases, some more use cases in the healthcare are already implemented in the field. I just want to give you a glimpse. Specifically, Google has done a lot of work specifically in the field of medical AI. And as I was telling you, Palm is a large language model developed by Google Research, and it is specifically designed for medical domain. And this a chatbot developed based on this medical palm, MedPalm, is already tested in Mayo Clinic, and the reports, very satisfactory reports, has come related to these response from these AI reports powered by medical palm. Now, large language models, you are already aware there was a dedicated session on large language models. So we'll only stick to the application side of these models. Like, so how these LLMs can be helpful uh, in healthcare, like what all tasks can be performed with the help of these LLMs. As I was telling you, we can have medical related foundational models, which can be reusable components. So with the same analogy, here also we can have medical foundational models trained on millions of electronic health records. Now, once they are trained on millions of data, uh, then what we can do is we can use these foundational models developed specifically for medical field. We can fine tune or we can adapt them for specific tasks like developing chatbots and summarization of reports or analysis of images, finding similar patients, and so on. And also we can develop different UI applications or the chatbots to perform these type of tasks where we have underlying medical foundational model fine-tuned to perform these specific tasks. Now, what kind of tasks we can have? So let's have more idea about it, like what kind of data we can provide to train these foundational models, and then we can adapt them for different tasks. Like we can provide different medical research papers, different clinical notes, medical textbooks or reference materials, different healthcare reports, education materials for the patients, and this data can be used, a large volume of this kind of data can be used to develop a foundational model, which is trained on existing data. And then this can be adapted for different type of tasks like generating patient summary, healthcare related question answering, translation from one language to another language, generation of text, medical related text. Now, another example here, see how the LLM has helped us. In the beginning, we took an example on ChatGPT, which was also powered by LLM in the background. Here also, you can see what we have, what kind of question we have asked here, like what is vitamin D3 used for, and should I take it? So this is what uh, a specific LLM, which is developed for uh, healthcare related question answering, and you can see it has given you a specific answer related to vitamin D3. Another LLM use case in the field of healthcare could be like generating an operation note. Suppose a surgery has just happened, and usually doctor make a lot of notes whenever a surgery is being done, notes related to history of the patient, notes related to what all operations has been done uh, during the surgery, what was the outcome, what was the complications, uh, what kind of experience was there during the surgery. So, with the help of LLMs, by providing minimal inputs, we can generate a patient note to a specific kind of surgery here. Now, there are different general purpose and specialized medical LLMs. You can refer to these LLMs and adapt them to specific problem in which you are working. So, like BioGPT, Clinical BERT, PubMed, BERT, Medical LM, Biomed LM, SciBERT, Image BERT. There are different specialized medical LLMs proposed by researchers, which can be used by other fellow researchers for different kind of research purposes. Now, as I was telling you, these LLMs could be of multimodal type. Not only whenever the term LLM comes into our mind, we only talk about uh, natural language processing uh, as an input and natural language as an input for these LLMs. However, here we can develop multimodal medical LLMs and which can be capable of handling text data, image data, any structured data or the video data. Like in text data, there could be different examples like clinical notes, medical coding terminology, patient instructions, medical research papers. In case of image, you can have X-rays, CT scans, MRI scans, the histopathology images, microscopic pathology images. There could be text data, which is structured text data like lab results, demographic data, and similarly, we can have video kind of data for surgical recordings, 3D medical records. Now, with the help of these multimodal medical LLMs, since these LLMs are capable of dealing with uh, multimodal medical types, and so different type of tasks, different capabilities they possess if they are able to handle multimodal medical data, like discover relationship across data types. Like these models can correlate findings in an image with text description in the corresponding report. So if it is a multimodal, that means we are providing, suppose, an image of the patient. I mean, the medical image like X-ray, CT, or MRI, and uh, we can also provide some kind of report to the LLM, and it can correlate the findings in both the raw image as well as the report. And in turn, it can improve the diagnosis, like detecting subtle abnormalities and suggest differential diagnosis. It can help in streamlining the radiologist workflows, like creating textual reports from the medical images. Now, whenever we go for any diagnostic test, the diagnostic reports are being developed by the radiologist manually. Why can't I mean, we can take help of these models to generate reports of X-ray, CT, or MRI automatically, and that can help the radiologist specifically. And also, instead of uh, generating these reports in complex medical languages, why can't they provide a patient-friendly explanation for that report? We need not to go to Google to understand those complex terminologies. And then another capability could be generating synthetic medical images with specific conditions or variations. As I was telling you, uh, you can give a prompt to develop and to create or to generate an X-ray image with symptoms of tuberculosis. So specifically, these kind of images can help us in augmenting your data set, and then further they can be used for developing new models, developing research capabilities. Now, one of the uh, multimodal LLM since I'm taking LLM as a generic term, and similar to LLM, we can have vision language models which are capable of taking vision as well as language input and process them together to generate different kind of content. So in this example, this vision language model is used for medical image analysis. It is capable of taking different type of visual modalities like X-rays, MRIs, and it can take different language models like visual question answers or report, electronic medical report, and they can pass through a different type of encoders like the language models modalities can pass through text encoder to generate the embeddings, and the visual modalities can go through can be passed through image encoder to generate that kind of encoding, and then further they pass through this fusion model where the image embeddings and text embeddings are fused together, and then we can perform different type of downstream tasks with the help of these embeddings as well as the fusion of these embeddings. Like we can perform detections, we can perform classifications, segmentation. Similarly, we can generate reports, we can generate have question answering related to these visual and language modalities, or also we can generate images based on these type of modalities. Now, one of the popular tools you have gone through this generative adversarial network, and this generative adversarial network is helpful in augmenting your data set. It is capable of generating new images. There are different medical related image analysis tasks which can be performed with the help of generative adversarial network like segmentation, reconstruction, augmentation, or detections. So basically, GANs are not only used for generating new type of image, but the whole model can be used for different tasks like segmentation or reconstruction, detections, and of course, augmentation. Now, as I was telling you, one of the major application of generative adversarial network is in for medical image augmentation, and I mean, we have already talked about the medical data sets having less number of positive samples in comparison with the negative ones. So with the help of these GANs, we can synthesize data set images, transform them from one class to another in a realistic way, and definitely this augmented data set can be helpful in developing new models and doing research in a specific field where we have very less number of positives. This is one typical example of generative adversarial network where we have a generator and a discriminator, and during this whole in this whole pipeline of generating and discriminating the real and fake ones, these two networks are trained, and so in such a way that the discrete the generator is capable of generating images which are very close to real one. And so basically this generator tries to fool this discriminator, and this in this process of fooling this discriminator, it develops a capability of uh, generating new images which are very close to the real ones. These are some of the examples of generative adversarial network based X-ray image generation, and they are realistic ones. Now, one of the popular image generation model is diffusion model. You must have gone through this diffusion model also, and here also the main aim is to generate new data from. I'm not going into detail related to uh, the mathematical foundation of diffusion model, since this session is more about using these models for different medical applications. So let me skip that basic part. So these diffusion model use cases, we can use these diffusion models for text to image, for image imprinting, uh, for text guided image to image, or super resolution, or for human face synthesis. Now, this is one of the example here where we are using diffusion model for generation of realistic chest X-ray images. We have given a text prompt with kind of symptoms that we want to see in the generated chest X-ray images. This text goes to the text encoder to generate the embeddings, and they go as the input, query key value input to this denoising unit. I mean, I'm sure you must have studied this when you were discussing the diffusion model, and then it can generate the chest X-ray with provided symptoms provided through the text. These are some of the examples of the outcomes of a diffusion model-based chest X-rays, and they are realistic one. And the good thing here is we are providing different type of abnormalities or type of symptoms, and we are able to generate images containing those type of symptoms. This is another example here, DALI-based image generation. This is like hyper-realistic AI-generated images for image being generated for upper and lower cheek skin lesion, and these are generated from DALI model. Now, this was a brief about how we can use generative AI models in the field of healthcare. I have given you a brief idea about whatever models you have studied, how you can use those models to solve different kind of healthcare problems, whether it is um, related to generation of new images where you have dearth of specific type of images. You can use these models to develop those, generate those images, develop data sets, and then develop new models which can be used for that particular type of disease diagnosis. We have talked about LLMs and how you can develop specific medical related LLMs which can be handy, which can be helpful uh, in different type of tasks in the healthcare setting. And we can have multimodal type of LLMs, which are capable of taking different modalities as input, and there could be fusion of different modalities to solve different type of medical tasks. Now, I just want to give you a brief overview of what uh, we do in the field of healthcare and how we are applying AI or deep learning or generative AI in the field of medical. So one of the application we have developed here is we have developed a system for urine sediment analysis. So whenever we go for a urine test in the lab, there are three components to it. One is the visual appearance, another one is the biochemistry based test, and the third one is the microscopy test. So what we have done is we have developed a system which is capable of uh, detecting different type of sediments in the urine microscopy images. So as a proof of concept, what we have done is we have attached a camera to a microscope and a slide is put on the microscope. The camera collects multiple images and those images are being analyzed with the help of developed uh, deep learning model. And you can see here, these are the examples where we are able to detect different type of sediments in the urine. These are microscopy images, and these dots are being put by the model which we have developed, and they are basically counting the number of WBCs, RBCs, epithelial cells, bacteria, crystals, cast on the urine slide. So this task is being manually done by the doctor while seeing in the microscope. This we have automated. So this was just the proof of concept. Now we have developed a fully automated microscopic urine analysis system, and which is capable of preparation of slides as well as generating the complete report. So these are other like these are RBCs which are being detected. These are different type of crystals, and one more application we have developed for silicosis detection. So this is a device, an AI-based portable device for detecting silicosis in chest X-ray images. And the idea here is this device basically reads a chest X-ray and it detects whether there are symptoms of silicosis in that chest X-ray or not. Silicosis is a COPD disease, which is prominent in the mining workers and specifically in the Rajasthan region. So this was a state government funded project in which we have developed this portable device which houses a compute facility and the AI model, and it is capable of taking X-ray images as input from uh, either digital X-rays from pen drive, or we can attach a digital X-ray machine directly with this device, and it can read the chest X-ray images, do interpretation analysis of those chest X-rays, give the results, whether there is a silicosis or not. Also, it highlights the impacted region in the chest X-ray. So I think that's all for today. Uh, if you have any queries, please let me know. I will be happy to answer those queries. Please type your queries in the chat box. If you have any queries, let me please answer those queries here. So if there is no query, I think we can conclude here. Thank you all for patient hearing. Thank you. Thanks a lot.
Thank you, sir.